Right, so before we carry on, it might be worthwhile just to also look at a quick example. Let us find there the orthogonal complement of W, and W is just given as the span of those two vectors, so it's all the linear combinations of those two vectors. So this is a very simple process. All we need to do is we need to find all vectors that are orthogonal to those to every vector in W. And we know the only way that happens is the vector has to be orthogonal to every vector in the basis. And that means that it has to be orthogonal to every vector, every one of those two vectors. Alright, so let's take a vector V in the orthogonal complement of W. Right, so that means that the only way V can be in the orthogonal complement of W is if it is orthogonal to every vector in W. Okay, so that happens only, like I said, when V is orthogonal to that vector and V is orthogonal to that vector. Okay. Right, so we can set up two equations from that information. Okay. Alright, and solving that, we're going to have to parameterize one of the variables. Right, so that implies we can let Z be a parameter t, and so we can solve for x and y as minus t. So the vector v then becomes the vector t minus t minus t t. All right, where t is a specific real number. So the orthogonal complement of W is the set of all vectors all right. And next we just have the Theorem 7, which states that if A is an m by n matrix, then the null space of the matrix A and the row space of A, they are orthogonal complements of one another. Also, the null space of A's transpose and the column space of A are also orthogonal complements in Rm. Now let's look at the first one, why that is the case. So if we go to a matrix, A, right, m by n matrix, and we look at the null space of that matrix, when is something in the null space of a matrix? We say this vector is in the null space of that matrix if this whole matrix equation holds. And when does that hold? It only holds when this row vector's dot product with that column vector is 0. Also, that row vector's dot product with this whole vector here's, that dot product has to be 0. And the last row's vector's dot product with that vector again has to be 0. So therefore, it basically is the same as saying that this vector is orthogonal to every one of these row vectors. And when does that happen? The only way that happens is if this vector is orthogonal to every one of the vectors in the basis for the row space of the matrix. So therefore, the null space of the matrix A will be the orthogonal complement of the row space of the matrix A. Right, next we check out the fact that the theorem states that the null space of the transpose of a matrix and the column space of the matrix A, they are both orthogonal complements in Rn. Right, so there we've got the matrix A, and we said the row space of A and the null space of A are orthogonal complements to one another. So the next one is easy to see. If you look at the transpose of A, then we know that for this matrix we know that for the matrix A transpose, we know that the null space of the matrix A transpose is the orthogonal complement to the row space of the matrix A transpose. Alright, so taking the row space of the transpose of the matrix A, and if we look at the orthogonal complement of that set, then that is going to be the null space. It's going to be the null space of the matrix A transpose. Now if we take the row space of A's transpose, then what do we know about the row space of A's transpose? The row space is the space spanned by the rows of A's transpose. These rows. And where are these rows actually? They are what in the matrix A. These rows are in fact the columns in the matrix A. Alright, so that's a space spanned by the column vectors of A. So therefore the row space of A's transpose is in fact the column space of A. So therefore we can replace the row space of A's transpose with the column space of A. So the column space of A and the null space of A's transpose, they are orthogonal complements of one another. Alright, let's quickly look again at an example here. Here they ask us to find a basis for the following four spaces. And they give the matrix A. Alright, looking at the first one there, let's find the row space of A. It's easy to do that. All we do is we reduce A and we get the following. We get that matrix there. Alright, and just taking it a little bit further there, we get the reduced row echelon form. So now it's easy to see what the basis for the row space is. The basis for the row space is the set containing these two row vectors. Right, so the basis for the row space is then the two row vectors. Alright, so the row space is basically the span of those two row vectors. So now how do I determine the basis for the null space? We know that the null space and the row space are orthogonal complements. So let's try and use that. Right, so the null space of A is the orthogonal complement of the row space of A. When is a vector in the orthogonal complement of a specific set, in this case this set? It's in the orthogonal complement only if it is orthogonal to every vector in the basis for the row space of A. So it has to be orthogonal to all the vectors in the basis. Right, so let's take a vector v to be in the orthogonal complement of the row space of A, or the null, in other words, the null space of A. Alright, and this happens only when the vector v is orthogonal to both the vectors in the spanning set. Right, from there we get two equations. Parameterize the variable z. It follows that x is t and y is 2t. It follows that the vector v has to be of the form the real number t times the vector 1, 2, 1. So it's basically a scalar multiple of that vector 1, 2, 1. So a vector is only orthogonal to both if it is a scalar multiple of this vector here. So now we know what the null space is. Right, so the basis for the null space is the set B subscript ms, and that is only the vector 1, 2, 1. Alright, next we have to find the basis for the column space of A. So we take the matrix A and we go and find its reduced row echelon form. And we said the reduced row echelon form is that matrix there. And basically now it's easy to find the basis for the column space. We know that these are the two columns that have the leading ones. And so that if we go back to the original matrix, those two columns identify what my basis vectors are going to be for my column space. So those are going to be the first and the second column respectively. Okay, so the basis for the column space of A becomes Right, so there we've got the basis for the column space. Alright, so let's find the null space of A's transpose. Right, so the null space of A's transpose we know is the orthogonal complement of the column space of A. So when is a vector in the orthogonal complement of a specific set, which in this case is the column space of A? It is in the orthogonal complement of the column space of A only if it is orthogonal to every one of the vectors in the basis for the column space of A. Alright, so what we're going to do is we're going to take a vector from the orthogonal complement of the column space of A. Alright, now we know that that only happens if V is orthogonal to every vector in the basis of the column space of A. Right, so I just want you guys to remember this, that the column space of A is basically the span of these two vectors here. So V has to be orthogonal to both these vectors. From that information, V has to be orthogonal to both those two vectors. From there we get two equations. Right, and we can then go and find a general solution for those two equations. Right, continuing, we get, so adding 1 and 2, we get 3x minus 5 equals 0, and then solving for x, we get a term for x in terms of y. Parameterizing y, we then set x as 5 over 3t. Right, so then from 2 we plug it into and get the value for z. So it follows that v is in fact a scalar multiple of this vector here. So now we know what the null space looks like for a vector v to be in the null space of the transpose of A, it needs to be a scalar multiple of that vector. Right, so the basis for the null space of A's transpose is basically the set containing that vector. Right, so take note that we can go and extend the equivalence theorem. Again, if A is an n by n matrix, then the following statements are equivalent. So we've got those, the first whole bunch of properties, and we can extend it by 2, which is to say that the orthogonal complement of the null space of A is the whole Rn. We know that the orthogonal complement of the null space of a matrix A is simply the row space. And the row space of A is Rn if and only if if A reduces to the identity matrix, and that happens if and only if A is invertible. Right. Then the next property is the orthogonal complement of the row space of A has to be the 0 vector. Now, if the orthogonal complement of the null space of A is the whole of Rn, we know that any set, if you have this a set W and the orthogonal complement of W, we know they only have the 0 vector as a common vector. So if the one set W is the whole space, which in this case is Rn, then the orthogonal complement of that set has to be the 0 vector. It can't be any other way than that. Right, so we can extend the equivalence theorem with those two properties. Okay, so I'm going to do one last example. I'm going to do the first example. And the second example I will leave as an exercise for you guys to do. So in the first example, let W be a subspace spanned by the given vectors. So the given vectors in this case is V1 and V2. Now what they want is, they want us to find a basis for the orthogonal complement of W. Okay, so we take the two vectors V1 and V2 respectively, and we form the set W, which is the span of those two vectors. What I'm going to do is, I'm going to form a matrix A, and I'm going to form it as follows. Let's take the vectors V1 and V2, and we form our matrix. We form it by taking the rows to be these two vectors V1 and V2. Okay, so recap, what is the orthogonal complement of W again? Right, remember W is the space spanned by the two given vectors V1 and V2. And the orthogonal complement of W is pretty much the orthogonal complement of the space spanned by the row vectors of the matrix A. So it's the orthogonal complement of the row space of A. And what do we know about the row space of A? The row space of A and the null space of A are orthogonal complements of one another. Right, so the null space of A is actually the orthogonal complement of the row space of A. Right, so this problem is equivalent to getting the null space of the matrix A. Right, so take the matrix A. Right, so the problem is equivalent to finding solving this linear system of equations that one gets from that matrix equation. All right, so from that system we can set up two equations. right? And we can go ahead and solve for that linear system. So we parameterize the variable z from 2x is minus a quarter t. Substituting into 1, we obtain an expression for y. It follows that the vector x, y, z, which is in the null space of the matrix A, needs it needs to be a scalar multiple of this vector here. Right, so the null space of A is basically all scalar multiples of that vector. Right, okay. Alright, so recall that the orthogonal complement of W is the orthogonal complement of the row space of A, and that's equal to the null space of A. Alright, so the null space of A is therefore this whole set that we said, which is that set there. Okay. Right, so what is the basis for the orthogonal complement of W? A basis is therefore going, the basis for the orthogonal complement of W is going to be pretty much the vector minus a quarter 5 over 2 1. Okay, so that answers